Now, good morning and welcome to today's lecture. Kindly confirm you can hear me and you can see my slides. Kindly confirm you can hear me and you can see my slides. Good morning, Helen. And good morning, Jerry. Now, so last week we stopped at layer 2, that is data link layer. We were trying to look at how communication is facilitated at that particular layer. And what comes out is that the communication at that layer, strongly depend on the MAC address, the media access address. Okay, and we said briefly as an introduction that that is the address of the network interface card, NIC. And is a 48-bit representation. And I did give you some task to go ahead and look at number systems. Also mentioned that you can get that content from Engineering Mathematics by John Budd. I don't know if you are in a position to get that. I don't know if you're in a position to get that. It's quite helpful because the slides that we're just going to go through is not going to explain in details the mathematics behind everything that we are talking about. So that textbook would have explained it further in terms of mathematics, what we are really looking at here. So my slide is just going to capture the exact point where we'll need in network communication. And the mathematics picture is captured in that book. So you can check with that book and maybe get further information. But if you had read through last week or before the class, then as well you can raise any questions that you might need some clarification or some aspects that you read through but you are not able to understand. Okay. So number system is chapter 5 of our chapters. I'll post the content there. You can as well read it at your own point. Okay. Now our objectives for this chapter is only two. Just looking at calculation between decimal and binary, and looking at calculation between decimal and hexa. Now, so it is hexa here that I mentioned that this is where the MAC address will come in. Okay. That's where the MAC address will come in. This is where also in future IP version 6, Internet Protocol version 6, will find its representation. But currently, the binary is used to do the representation for IP version 4. Now, the reason why I was insisting that you go and read that book is because there's a lot of that type of mathematics is really coming up in representation of IP, the Internet Protocol, okay? Where now that is the address, or that is the communication pathway in the network layer. There's a communication pathway in the network layer. So there's a lot of such kind of mathematics that are coming up. So we want to look at these basic conversions. Look at those basic conversions, then we can move on with the other components. Now, so as I mentioned earlier, we have three types of addressing. We have MAC address. We have IP addressing V4 and IP addressing V6. Okay. So binary number system. I'd mentioned that in number systems, they are defined based on what we call the base. And it's fortunate that all of us know what a base is. We've done logs, okay? So they're defined based on what we call a base. The base represent the number of items, if I may call it so, because like as the hexadecimal will not have numbers only. So represent the number of items in that particular number system. So for binary number system, there is the original number system for computing. We have two items, 0 and a 1. And we call them bits. So when we group these bits, a mixture of 0 and 1s, not in exactly a specific format, but even randomly, okay? Even randomly, then 8 of them should form what we call a byte. 8 of them should form what we call a byte. And it is very, very important as a student that is pursuing a professional course in one of the leading industry providers, that is Cisco. You know that in computing, byte is an SI unit for storage. Byte is an SI unit for storage. So we'll talk about my hard disk is 20 GB. That B there is byte. When you talk about communication, we talk about bits. We talk about speed of the network. My network is running at 5 Mbps. Mbps, megabits per second. Okay. So if your network is running at 1 GB, then it's going to be gigabits per second. Okay. Now, for decimal number systems, the items contained are from 0 to 9. Therefore, because they are 0 to 9, you count them physically. You get 10. So meaning that the base of the binary of the decimal number system is 10. That is computed from the number of bits, from the number of digits in this case that are found in that particular number system. For binary, it's going to be 2 because we only have 2 items. Now, so the conversion between bits and bytes, not bits and bytes, but binary and decimal, is basically to ease the process of human understanding. Okay, to ease the process of human understanding, so that we can be able to communicate with the computers. When the computer speaks bits, we can translate them into our digits that we understand very well. Okay, so these bits are used in identification of computing system. You talk about CCTV cameras, you talk about IP phones, you talk about the computers themselves, you talk about laptops. Okay, so they're used for identification purpose. Now, so how do we address these issues? We've agreed that binary is just a mixture of zeros and ones, purely. They can be as many as you can or as many as you want, provided you are representing something that is logically allowed in computing. Now, so we go back to class 3 or class 4, somewhere there, or class 6, and you remember what we used to call place values. The ones, tens, 100, 1,000, I don't know whether it moves 10,000, I'm not sure. But now that reflection, okay, that reflection is what we are using here. Here we're not going to call it place value. We rather call it positional value because we are going to refer to a bit or a number based on its position in that combination of numbers or combination of bits. So we are going to call it positional values. Now, radix here is similar to the base. The word radix is synonymous to the word base. Okay. So there are calculators that can be able to do these things randomly, or can be able to do these things automatically. But now you need to understand what the calculator does for you to utilize the information that the calculator is going to give you. Okay, so an example is given here between positional value and place value, or whatever, place value, as we used to call it back then. Okay, so if this is the decimal number, we have 3210. We have 3210. Then we begin to assign our positions from the right. I'm sure we all know that. So position 1, position 2, position 3, and position, not position 1, but sorry, position 0, 1, 2, 3, 4. Now, so we relate that with the power in our calculation process. we'll relate that with the power in our calculation process. So that we say this position is power 0, power 1, power 2, power 3. Okay. So that's very important. So that this table is what is being converted, this one, okay? It's just the same thing that is being converted. Just explaining more and more about the position of values, okay? When now you talk about the place value, tens, ones, hundreds, thousand, that's how they are coming up, okay? So it's like 10 raised to power 3, okay? You get 1,000, okay? But now that is not of our interest. Our interest is, do you know how to assign the position of values? That's final, okay? Positional values are assigned from right to left, beginning from 0. And what are we going to use this position of values for? They are going to be used as powers in our expressions. When we want to convert binary to decimal, or decimal to hexadecimal, or hexadecimal to binary, whichever form that you'd want us to follow through. Okay. So the most important thing there is positional value. Now, so if you're doing the conversion, then the base of that number system is very important. The base of that number system is very important. Now, in binary now, our base is going to be 2, what we call the radix. And because in binary, we can only make up to a byte, which is 8 bits, okay, which is 8 bits, then that means our position of values will always run from 0 to 7. So as we assign position of values to the bits that we have, it will always run from 0 to 7. Reason being, we can only make up to 8 bits. So if you want to treat more than 8 bits, then we'll have groups, what we later call octet. Octet. So we'll have those groups of 8 bits, 8 bits, 8 bits. In other words, we have 1 byte, 1 byte, 1 byte. If you want to treat more bits. Okay, so if you do the conversion, this is what you get. If you do the conversion, that is what you get. So meaning a bit at position 7, is equivalent to 128 in decimal. A bit at position 6, 64 a bit, and it is because we are raising 2, which is the base, to power 7. 7, which is the positional value of that bit at that particular position. Okay. Now, if you look at the table 2, let me call it table 2. You look at table 2. What we're doing here is we are looking at the equivalent of this binary number. If this is a binary number, okay, that is a binary number with 8 bits, then we're looking at the equivalent of that in decimal. So you can go this approach. assign position of values, then you add them together. So what was the result at position 7? 128. Results at position 6, 64. Result at position 5, 0. Why do we say that is 0? Why do we say that 0? In the conversion procedure, which is expressed here, though not expressed so well, but in the conversion process, what we normally do is that if we're converting binary to decimal, we say, like, in this is our binary, we've assigned our position of values, and we know it is up to position 7. So if we are to begin there, then I'll say 2, which is the base of the binary, raised to the power, which is the position of value, times the by bits at that particular point. So in our case, it is 1. Okay. Then you add to the next computation, which is at position 6. 2 raised to power 6 times 1. Then you add to the next position, which is going to be 2 raised to power 5, but the bit at that position is 0. Okay? The bit at that position is 0. Now, if you add all this together, the computation continues until position 0. If you add all that together, the number that you're going to obtain is the equivalent of that set of binary number in decimal form. Okay, in decimal form. So as a mathematician, what you do is that if you're given a binary number, then you know very well that when the bit is 0, there's no result that is going to come out from there, because you're going to multiply by 0 and get a 0. So what you do, so that you move very fast, look at the binary number, assign the position of values, but only deal with bits that are 1. Okay, we call them high bits. Deal with only points where we have a high bit, 1, 1, 1, 1. The zeros ones will not return any result. Will give you a 0, obviously. Okay, but now this is the structure if you want to convert bits to decimal. So that is what is being done here, so that they are getting 192 from this. Okay. So why are we giving the 128, 164, 32, and so on and so forth? These numbers here are the ones we'll be using in computing. These are the ones that are of interest to us, especially when we'll be dealing with the IP. Those are the ones that will be of interest to us. So examples are here. You can see that converting binary to decimal, what I've just mentioned there. Okay, so if you're given a binary number like this, just assign the position of values. We all know our position of values basically tagged to these numbers. Okay, so do that for each. So the next binary is that. So position number 1, position 0, 1, 2, 3, 4, 5, 6, and 7. Okay, then do the same thing. Okay, that is actually what they are doing here. Then they're adding them together. Okay, So at position 7, it is 2 power 7 times 1. At position 6, I said where there's a 0, we don't even need to struggle with that because we'll multiply by a 0 and get a 0. At the next position is position 5, that is 2 power 5 times 1, which is 2 power 5 is 32 times 1 is 32. Then because others are zeros, we are not interested in that. They are not making sense to us, okay? Then the next one is a 1, which is of interest to us. So it has position what? Position 0, 1, 2, 3. So it is 2 power 3 times 1. We get 8. So 8 is of interest to us. Then we add everything here. When you add that, you get 168. The same thing happens here, you get 11. The same thing happens here, you get 10. So after you've obtained these decimal values, if you go to your computer now, and you type maybe a command like ipconfig, okay, you type ipconfig, you'll be able to see an IP address maybe for your machine. Okay, that IP address is computed like that. This is how the computer will understand that number. But for you, it will be written as this. Okay, so meaning that is how the computation. So if you want to put that in binary, then that is how it should look like. It should be 110000 dot the next one 10010101000 dot and so on and so forth. So these pieces here is what I'm calling the octet. A set of bytes. So this is 1 byte, meaning 8 bits. This one is another 8 bit. This is another 8 bit. This is another 8 bit. So it is 8 plus 8 plus 8 plus 8. So an IP address, especially version 4, is 32 bits. 32 bits or 4 bytes. But now it's not a term that is allowed in the industry for you to tell somebody that an IP is 4 bytes. So we normally say it's a 32-bit string or a 32 bits set of bits or binary numbers. So you can put something down if you are writing. So when I pause, you can pick whatever you can be able to pick from the slides that will be of benefit to you. So you can move on. So that's how you do the conversion from binary to decimal. That's how you do conversion from binary to decimal. Now, for decimal to binary conversion, I'll summarize it in a mathematical way. What normally happens is that we always do what we call a long division. Maybe from that, you'll now be able to understand maybe the methods that is being implemented by Cisco here. But now what happens is that we do a long division. Okay, so how does a long division works? For instance, if you're given 128, and we say that's a base 10, meaning it's a decimal number, and you're required to do the binary conversion. What happens? Just divide this by 2, which is the base of the binary. Then you record your remainders. Okay, you record your remainders. So as you do the division, if you do the division, so somebody can do the division and give me the answer. So our remainder is there. So maybe I can give you the first one. 2 divides 128, 6, 4. And our remainder is 0. Because 2 times 64 is 128. There's no remainder. Next is 32. 2 divides 64 32 times. Remainder is 0. Okay. Next is 16. Remainder is 0. Okay. Next is 8, 0, 4, 0, 2, 0, 1, 0, 0. Remainder is 1. I don't know if you've gotten that step, the last step especially. Okay. So 2 divides 1, 0 times. Remainder is 1, because 2 by 0 is 0, and therefore remainder is 1. Don't know if you've gotten that concept. Now, once you do this, we normally say, read your content in upward direction. Read your content in an upward direction. So meaning, begin with 1, then you read the, how many zeros? 1, 2, 3, 4. So 0, 4 zeros. Okay. 1, 2, 3, 3 zeros. Okay, so in other words, this one we can say base 2 because it is in binary, but in networks we don't usually put the base. The base is very important in mathematics. In networks we don't do that. So in other words, what we have is 0, 0, 0, 0, 0, 0, 0, 1. So this is the equivalent of 128. And if you check our previous conversion, then if you assign position of values here, 1 will be at position 7, and 2 raised to power 7 times 1 is 128. And I said, where there are zeros, you don't even need to consider that mathematically, because you know very well where we're going to land. If you multiply by a 0, really we are not moving anywhere. So you get 128. You can put base 10, but now, as I mentioned, in networks, our bases are not really important. Okay, that is how you convert your decimal to binary. That's how you convert your decimal to binary. Any question? So that conversion will move in that direction forever. Even if you're doing mathematics. Question? Any question? Any question? Now, so you can maybe you can read this one on your own at some point, but it's talking about the same thing I've just mentioned, and what I've mentioned is mathematically more accurate and not accurate really, but more direct rather. Okay, everything here is accurate, even the C-score way is accurate, but this is more direct compared to this one. But you can read at your own time and be able to find out which one do you prefer. Any question? So as I mentioned before, if I'm moving the slides so fast, maybe and there's something you're writing, then you just let me know. Just notify me so that I can allow you do the writing further. Yes, if there's no question, let's proceed. So those are examples that you can try on your own. Just try them on your own and see if you'll be able to understand. I'll post this slide. So that's what I was telling you, that's how we represent IP version 4 addresses. Now IP version 4 is are basically an identification mechanism for communication in layer 3. We'll look at layer 3 later. Okay, but that's not what IP address is supposed to mean. So we'll dig deep into IP and really find out the classes of IP, how they relate with one another, types of IPs. So we'll dig into that later. But that is the mathematics here is very important. Okay, so that's a representation there. So you can see that you can decide and just put a dot there, a dot there, and a dot there, and you're still ready to go. Okay, but that's how the representation that an IP should look like. So hexadecimal, which is, as I mentioned, a very important component in IP version 6 and MAC addressing. So I'll expand for you to see, especially the tables. Okay, so I hope you can be able to see the tables very well. So check the comparison that is there between decimal, binary, and hexadecimal. Check the comparison that is there. Okay, so hexadecimal has these letters. There. So you check these and you realize that the hexadecimal is a bit expanded. Okay, the hexadecimal is a bit expanded. So hexadecimal represent 0 up to 15, with 10 up to 15 being represented in letters. So what is the advantage of that? The advantage of that is that we're expanding the range of numbers that we can be able to do. Okay, so we have up to 16 items that we can represent. Okay, so we are saying it is easier to express a value as a single hexadecimal digit in comparison to a 4 binary bit. Okay, in comparison to a 4 binary bit. So what is the base of the hexadecimal? As I mentioned, the base is derived from the number of items that are supported. So we have 16 that is supported. So that means the base is 16, or the radix is 16. And I mentioned that this is very important in MAC addresses and IP version 6. MAC addresses and IP version 6. So in mathematics, these tables here are always calculated, but for us in networks, we're not really so much on the calculation, but very important, especially when I'll introduce a bit of subnetting, okay, a concept known as subnetting later in the chapters towards the end of the whole course. Now, so very important to note is that here we are working with 128 bits. Look at that. 128 bits. And each, for every 4 bits, we use 1 hexadecimal digit. So therefore it means 128 divided by 4 you get 32. So that means an IP version 6 address is a total of 32 hexadecimal values. Okay, so a case represented on this side here, just showing you how you might just be able to represent that. Okay. So in moving forward, we'll really appreciate the opening up of the length of the IP version 6 all the way from 32. Remember the other side we were having a length of 32 bits, 8 times 4. But now here we're having 128 bits. That means 4 bits per hexadecimal digit. 4 bits per hexadecimal digits. Now, the mathematical conversion will remain the same thing. Mathematical conversion will almost remain the same thing. So that is how the process should move like. If we were to do the conversion, that's how the process should move like. So you convert the decimal to an 8-bit binary string. Okay, so you can pick those steps or you can just have a look at them. Okay, so this similar process can also be obtained by the same method I've just introduced in the previous chapter. Anybody who went through this content that I'm walking through? Because I'd say that you go and do the same last week. Anybody who did that? Anybody? Okay. So that's not really encouraging. If you are given some work to do, it's always good to pursue it, okay? It's always good to pursue it. Now, so I'm saying that this process we mentioned here can also be obtained through the mathematical calculations I've just mentioned there. So like maybe if you have this number here, let's say that is the number. How did we convert decimal to binary? How did we convert decimal to binary? If you were given like 128, we said you do a long division and you record your remainders. Okay, so the same thing will happen here. If you want to do a direct method in mathematics, you just pick 168. Just pick 168 and divide by 16. Divide by 16. So this is going to be a little bit tricky. You'll need to maybe use a calculator for you to be able to find out. Okay, for you to be able to find out. So somebody who can divide that and give us the answer. Somebody can divide that. So we all know that 16 is going to divide this one 10 times. That is 160. Remainder is 8. Okay. Remainder is 8. Then 16 divides 10. This is 0 times. So 0 times 16 is 0. Remainder is 10. From our chart, or if not from our chart, we agree you read this going forward. So if you read that going forward, or upward rather, you get 10 and 8. And we said in hexadecimal, from 10 going up to 15 is represented in letters. So 10 is equivalent to, our 10 is equivalent to A. And therefore, we'll get A 8. Okay, so that's a process that you can be able to use that is maybe more direct. You can, rather than converting to binary, then putting them into 4 bits and so on and so forth, then reading out again. So you can decide which one works for you. You can always decide which one works for you. Okay. So the opposite is also true. just the same way we were converting binary hexadecimal numbers to binary, not hexadecimal, but binary numbers to decimal. So if you're given 8 raised to power 16, which is a decimal, an hexadecimal number, then you can definitely convert that to decimal by easily doing the reverse. So instead of dividing by 16, you put the position of value, so that is going to be 0. This is going to be position 1. Okay. Then from there, just perform the same thing that we did in the reverse order, the other side. So we'll have A times 16 raised to power 1. Then plus 8 times 16 raised to power 0. Okay. So this is going to be, A was 10, so it's going to be 10 times 16, which is 160. Then plus 8 times 16 raised to power 0. And from our indices, we know anything raised to power 0 is 1. So 8 times 1 is 8, so plus 8. So 160 plus 8 will definitely give us 168. And there, you're already back in decimal number that you are given initially. Okay, you're already back in the decimal number that you are given initially. Any question? Any question? Any question? So the other number systems like Octo number system and the rest, but that is not; those ones are not important for us. You can just have a look at them, maybe just to enhance your understanding of where computing has come from. Or you also do them as part of what maybe we call digital logic later in a different unit, just to find out the operations of different logical circuits, the flip-flops and the rest. Okay, so any question on decimal to hexadecimal, hexadecimal to decimal? There are two methods there. You can choose whichever you want to use or whichever you feel comfortable with. Any question? So the other method is here. I've just done the mathematical one. The process one is here. You can just have a look at it. You can just have a look at it, take the notes. Any question? Any question as far as that conversion is concerned? So you really need to understand those conversions, because you really have a big trouble understanding IP addressing, because we'll not be looking at how to do the conversion. We'll just be rushing through other very important issues on IP. So it's very, very important that you get the conversion process very, very well. That's why I took time and went through these slides, despite maybe having given you that work to do at your own time. But I realized that we might move into IP addressing, and some of us still do not understand that conversion clearly. Any question? Any pressing question? Any pressing question? Yes, so if there's no question, then we can finish up our, the lecture that we were working on last week, so that next time we do something different. So we left at frames. So frames are basically communication paths in communication paths at data link layer. Okay, so that's why I was wanted to introduce the concept of MAC address, or the concept of binary mathematics, so that you understand when you talk about the MAC address, you know hexadecimal, what do they represent. Okay.
Added destination, added preamble and frame check sequence, and therefore it is no longer a packet as it was in the topper layer, but now it is called a frame. So why it puts all of this is to make sure that this data is able to arrive at the destination. So we have been talking about MAC address, MAC address. What is this MAC address? Now, first of all, MAC address is 48 bits. So a MAC address, like we say, IP is 32-bit. I know we haven't gone deeper also into IP. Humor me, we'll reach that. Now, a MAC address is 48 bits. MAC address is 48 bit and is divided into two. So let me type something. So the MAC address is 48 bits divided into 24. And the first 24 is called OUI, Organizational Unique Identifier. And the second 24 is vendor assign. What does that mean? Let me try to explain here clearly. Here is saying that, for example, if I have a device, I have another device, and let's say here also I have another device, So let's say these red devices are HP. These purple devices, or pink devices rather, are Lenovo. The first one that we say is OUI, Organizationally Unique Identifier. It means that it's going to, first of all, they buy it from IEEE. So if IEEE say, okay, you, HP. So let's say you, this guy is HP. And let's say this guy is Acer. So you buy from IEEE. The first 24-bit will be assigned to you. So if you open an Acer laptop, another Acer laptop, the first 24-bit for the MAC address would be the same. The last 24-bit can be different, and that is what we uniquely differentiate this from this and from this. When you open that of HP, the first 24-bit will also be the same, saying that this is for HP, and the last 24-bit may be different to identify this, this, and this. So by looking at the first 24-bit of this versus this, you're able to say that this is a different vendor, and this is a different vendor. So with that, okay. So we said it is 48-bit, something like this. 1, 2, 3, 4. When you calculate it, they are out to 48-bit. The first 24 bits, so each 4-bit is one hex set. Each 4-bit is one hex set. So 1, 2, 3 up to 24 is uniquely organizationally unique identifier, which is going to be the same for HP and also the same for the different as from Acer, different from Lenovo, different from, so every vendor, the first 24-bit will be the same. And the last 24-bit will be different. This is what will uniquely identify the device. So let's look at this. What really happens if you're trying to process a document? Let's let me go. Okay. So I have a device. This is let me put my sketch. Okay. So we have 1, 2, 3, 4, 5 devices, for example. In the network interface card of this, when it's being manufactured, the vendor put A. The vendor here puts B. The vendor here puts C. The vendor here put D. So the MAC address here, when it was manufactured, is A. This is B. This is D, and this is C. When this guy is sending to this one, it will say the source MAC address is A, the destination MAC address is B. So when it comes into this, it knows that the communication is unicast because I know the source, I also know the destination, so it will forward it. When it's coming from A and it's going to D, when this switch receives it and sees that the source is A, the destination is D, because they are in the same local network, it says it's coming from A, so I'm going to send it to D. And that kind of connection is called unicast. A unicast connection is when it has a source and then it has a single destination. We say a communication can also be multicast when it's going to group of devices. Take a look at this. Now, in real sense, when you have, let me put packet choice. In real sense, when you have a device, and a device. Let me zoom for a bit. So when you have a device here and here and here, and let's just say, let me just put something short here. Let's say the IP address of this guy is 1.1.1.1, and the MAC address is A.A.A, whatever. And here the IP address is 1.1.1.2, and the MAC address is B.B.B. Example. And let's come to here, the last PC. The IP address is 1.1.1.3, and the MAC address is C.C.C. So the IP address is .1, IP address here is .2, and here is .3. Now you have a switch. Don't worry, I just want to use this to explain the remaining slides. So I'm bringing that to 2960. You have a switch. So you have your connection. You have a connection from this one to this one, this one to this one, and then this one to this one, to your switch. If you sit here on the application layer here, you come here and say you want to test connectivity, for example, and you say ping 1.1.1.3. Now, what is happening here is this. What is happening here is this, that if you say ping 1.1.3, look at what we find. Please just follow on. The source IP is 1.1.1.1. The destination IP, we say, is 1.1.1.3. The source MAC address is A.A. or as I put it like this, A. The destination MAC address we don't know, so it's going to be question mark. Let me explain what is happening. What is happening here is this. You are sitting here, so this PC already knows its IP address. It knows its MAC address because it's assigned to it. And you now ping 1.1.1.3. So we have found 3 things. We have found the source IP because you are sitting on this PC. We have found the source MAC address because you are sitting on this PC, and you say ping this, so it knows where it's pinging to. It's coming to this PC. But it doesn't know that what does this vendor have. You don't know whether the vendor assigned C.C.C or D.D.D or E.E.E. So the destination MAC address is going to be question mark. What we do here is that this information will in the data link layer, it will assign source that I know my source. The destination, I don't know the destination, so I'll put a question mark. So what it's going to do is it will send the information to the switch. Automatically, this question mark, or in some documentation, you see it as all F, automatically upon receiving all F, meaning broadcast, or the question mark, it means broadcast. We said a communication that is broadcast, it means that sent out to everybody. What this switch will do is, it will then it has taken in your information, but so it knows where you are. If the port here, let's say, is connected to port 1, this is connected to port 2 on the switch, this is connected to port 3. The switch has something called MAC address table or content addressable memory table, CAM table. It will say on port 1, port 2, port 3, assuming you have only 3 ports. It populates upon receiving the information. So when it receives the information from this PC to this switch, you say, I am receiving an incoming information on my port. That's what the switch will say. That is port 1. And the source MAC address is A.A.A.A. So I know now that A is attached to my port 1. Anything I see destined to A, I'll just send it to port 1. But the destination of this information says it's question marks or all F, meaning it's broadcast. I don't know where it's going to go. So what the switch will automatically do is it will generate a broadcast. The switch will generate a broadcast. Its broadcast means that it will send the information here asking, are you .3? The same time, it will also send the information here asking, are you .3? Any one of you that is .3, give me your MAC address. So this guy IP address is .2, so this guy will not reply. This guy IP address is .3, so this guy would then reply with his MAC address. Upon replying, remember, the MAC address table gets pulled upon receiving information. It says, I am receiving an information from C.C.C.C. Which port? It says it's port 3. Now it knows that C is in port 3. So upon receiving this, it goes back and informs this guy that this IP that has the 3, the equivalent MAC address is C.C.C. Then it will now forward the traffic. It does broadcast when it doesn't know the destination. But when it knows the destination, it does unicast. And this broadcast is for the first time. When it's sending for the first time, when it doesn't know who is attached to port 3, it will do this broadcast to identify. But subsequent communication from A to C, it will be unicast. But when it's trying to identify 2, because it doesn't know 2 also, this guy is still blank, it will do broadcast. And when it identifies 2, when A wants to communicate to 2, it knows the source MAC address is A, destination is B, it will just do unicast. It will maintain this connection until you remove a cable from this. When you remove a cable, it will reset this port. It means it would have to learn whoever is connected to again, because it doesn't know whether you are the one that will come back or somebody else will connect. Or after 5 minutes. After 300 seconds, equivalent to 5 minutes, it wipes out the MAC address table to learn it again to protect itself against hackers. We may get deep into this. So keep digesting this while I proceed. But when I come to it, I've used this to explain many slides. When we're moving deeper, I'll be talking about it in case my network break while we're at it. So as you can see here, it says it can send out broadcasts if it doesn't know the destination to identify the destination MAC address. But when it does, it will be sending it directly to the destination. So we have also, remember when I was even talking earlier about connection, I said that the devices that do unicast is our own connection. Like if I open my WhatsApp, I'm communicating to you, most of the times it's unicast, I know where you are. But the technology, some of them use your multicast, some of them use broadcast. So they use broadcast if they are to communicate to everybody. For example, in the case of address resolution protocol, ARP, which is a means of identifying the MAC address associated with an IP, or when it's STP, or DHCP, or as the case may be. So this MAC address table, every switch has a MAC address table, just like we have exemplified earlier. And this is there sometimes. So if this is a switch, if this switch is connected, it has port 1, port 2, port 3, port 4. This switch will maintain a MAC address table to identify what is the MAC address of whoever is connected to port 1, what is the MAC address of whoever connects to port 2, port 3, and then port 4. But we said that in the first, when you on your switch, by default, it is blank. So the MAC address table, this is for the port, this is for the MAC address is blank, but it knows that it has 1, 2, 3, 4 port, or 8 port, or 200 port, or 24 port, or 48 port, as the case may be. But when any one of them initiates a connection, for example, from here you say ping something, upon receiving the information ingress as it's coming in, it will run your MAC address and say, on this place, I have this MAC address on port 1. If it doesn't know the destination, it will do broadcast and ask, whoever have this IP, please give me your MAC address. If this guy replies upon receiving, it will also populate and say, in port 4, I have this MAC address. So subsequent communication between this one and this one will be unicast, no need to be doing broadcast. But if it's trying to identify 2 and 3, whoever is connected to them, it must follow this process. The process of doing this broadcast to identify a PC or a device connected to using its MAC address is known as ARP, Address Resolution Protocol, using the IP to identify the MAC address of a device. Every device that is able to connect to a network has MAC address, which is assigned by the vendor when they were manufacturing it. So moving further, say I have my switch. How do switches forward this traffic? Let me go back to this slide. Let's say, remember we said in a link we can have a bandwidth. We said 2 MB per second, 10 MB per second. So let's say this switch is connecting 1, 2, 3, 4 devices, and the link is all 1 MB per second. So, and I'm trying to send hello. And I'm trying to send hello. Hello, let's say hello, every character here is 1 MB, which means this cable will take 5 seconds to move hello from the PC to the port. It will also take 5 seconds from this to arrive here. How does it do it? We said it follows 2 methods. We have store and forwarding, cut through, because you cannot take the whole hello. So you have to send H first, then send E, then send L, and then O, because the link can take only 1 character. Assuming it's not a character, it's a bit of string. It has to be converted to binary, but just for us to understand it. So where is it going to be saving? Number 1 option, it says, when I receive the first H, when I identify the destination, when I receive the first H, I will just send it. It will keep H. When I receive the second E, I will just send it. It will put E. When I receive the third L, I'll send it. It will receive L. When I receive this one, I'll send it. The last one, I'll send it. And then finally, the destination device, we see hello. And this is what we call fast forward. So this is what we call, cut through switching. So as it's receiving, it's sending. As it's receiving, it's sending. Another option is the store and forward. The store and forward says that, no, you will receive everything first in the switch. So the hello will remain in the switch until I receive all the information before I'll start sending it to the destination. Why would I want to do that? For example, for some sensitive network, they say when I receive it, I'll check it for errors. If there are no errors, then I'll send to the destination. But this is slower. Sometimes if you connect to the network, most of the time you see that it will be downloading small. The pages, the texts will be downloaded, the images, and then the video, which is what? Cut through. As it's receiving, it's sending to you. It is building on your end. But the other means is saying store and forward, which means that when this switch receives all the information first, then it forwards it to the destination. So this store and forward, we said it will store it, check it for error. If it's fine, then it's sent. If it's called untrue, when it receives, it sends. So this code true, sorry, I keep saying code untrue. This code true switching is also divided into two. We have fast forward switching under code true and then fragment free. Now, fast forward is saying that the moment I receive, I'm able to just get the destination and send. Fragment free is saying, well, I want to check for errors and then I want to send as fast as possible. So I will not just send upon receiving. What I will do is when I send, I'll wait until I build up to 84 byte because most of the errors occur in the first 64 byte. So if I take the first 64 byte and see it's fine, I assume that the rest is also going to be fine. So then I'll start sending. But the basic thing you need to know is either store and forward, it keeps it, store it on the switch, and then eventually send to the destination when it receives everything and check for error. You have code true, which will assist receiving, it is sending, and which is divided into two. Either receive and send, or receive for some time, to up to some byte to check for error and say, well, if the beginning is okay, the rest is also okay. So where does it save it on the switch? It saves it, we have the port-based memory, whereby it saves it on the port. The problem of saving on the port is that it queue up everything. If the port is busy, it will have to keep queuing up the information as it's coming. So one information going to destination B can slow down the information going to destination C. But it can also have a shared memory like a temporary storage switch where it as I said, it depends on the capability of this, the meaning that it can send, it can receive, but one at a time. Then it also have full duplex, whereby it can send and receive at the same time. So your interfaces can be configured to be half duplex or full duplex. Now, even though we have said that we have moved past half duplex, we could have a scenario whereby you want to connect your interface to be half duplex. Also, what you need to note is any switch you see that the interface is gigabyte, not megabyte. It is by default full duplex. So let's say this is a switch. So we know a switch can do full duplex. And let's say this is a hub. Maybe I go to an old organization that still have hub. And it does half duplex. So you see, since this is a full duplex and this is a half duplex, there will be mismatch of speed. One is sending in full duplex, which is the switch, then the hub can only attain to half duplex. So you can change the configuration of your switch to step down into accepting legacy devices, old devices, and make the port to half duplex so that it can connect to a hub. That is if you were able to go to any network that still have a hub. And that will be a very, very old network. So that is the speed really. So you can dial it down to where it can both have duplex, because half versus full cannot communicate. So we also have auto MDIX. When we're talking about copper, for example, the unshielded twisted pair, we said that it's the most common connection copper cable. We said that if you terminate it as standard A, standard B, based on how you rearrange the column, if one end of the cable is standard A and the other end of the cable is standard B, you are creating crossover cable. And to create a crossover cable, it means you are connecting similar devices. Or if you are going to connect, if you connect one to be A, the other end to be A, or one to be B and the other end to be B, and we said that kind of connection is straight through when you're connecting not similar devices. Most of the times, the devices we have nowadays are configured with auto MDIX. And this auto MDIX, which is for medium dependent interfaces, it doesn't really matter whether you connect them using a crossover or straight through cable, it automatically adjusts by itself. So let's say I'm going to connect a PC to a PC, But instead of me to use a crossover cable for it, I use a straight through for it. So if you're using a straight through for it, it was supposed to give you a problem. But because of this feature, it automatically adjusts itself and then it works. So sometimes you may go and say, why do I connect to a switch using the wrong cable, as I've read, and it works? It's because of Odo MPX. But where you will run into problem is if you take old devices that don't have this feature, or when they have been disabled on the switch, for example. So you're never able to have access to that. So after talking about this media, data link layer, the topper layer is the network layer. It doesn't have much things to talk about here. The physical layer handles about the company, the connection, the RJ45, the SC connector, the BNC connector, the type of connection and termination. How is it being encoded? How is it being patterned to be able to be sent, or whether using the wireless or using the cable? While the data link layer handle connection within a local network, so it assigns the source MAC address and destination MAC address. We say MAC address is 48-bit, 24-bit uniquely assigned. So HP first bit should be 24. And by the way, if you want to see the MAC address of your device, of your laptop, you can click on your Windows key and search for CMD. In the packet tracer, I will click on desktop, and this is CMD. Or you can click your Windows and search for run. When it opens, you type this ipconfig/all. If you just say ipconfig, you will only see the network interface card that you have, like whether like this one has Bluetooth and it has also Ethernet, but it doesn't have wireless. So, but if you said ipconfig/all, it says it gives you everything. ipconfig/all, including the MAC address. So when you see its physical address or MAC address is the same, it says this is the MAC address. So the first 24-bit is for the organization, the last 24-bit is for the vendor. So if you have a HP, this first 24-bit should be the same for your devices. Okay. So moving forward, it says, so in data link layer, so you identify the source MAC address because it's its own, and the destination MAC address because it's on that device, and it doesn't know it will send an F in the column for the destination MAC address, and when the switch receives it, they will know that this source have all the information except for the destination MAC address. So the switch will now set the broadcast asking all other link on itself connected to it, asking whose IP is this, and if you are, send me your MAC address. Somebody is trying to communicate to you. That process is called ARP. So here in the network layer, it's talking about IP, Internet Protocol. This is the internet itself. It's focused on IP, and it has two versions. We have the IPv4 and the IPv6. So basically, the network layer performs 4 basic operations also: addressing, which means assigning source IP, destination IP, just like data link layer will assign source MAC address and destination MAC address. It also does encapsulation, which means from network layer it will encapsulate it. From transport layer it will encapsulate it into network layer, which is called a packet. And when it comes down here, data link layer will encapsulate it into a frame, and this one will encapsulate it into bit or stream. So it does also routing, moving traffic from one network to another, from one end to another. Let's go a bit deeper and see. So the upper layer here, we said in general, wherever the information is here, we call it PD, protocol data unit. But in every layer, it has a name. We say here, bit of stream bits. Here we say frame. Here we say packet. Here is called segment. So when a segment is transitioned, is encapsulated down to network layer. So it's going to come as segment, and network layer will encapsulate it into packet. And when it's encapsulated into packet, it will send it to the next layer, which will encapsulate it into frame. And this layer will encapsulate it into bit of stream. So what is this encapsulation? I receive a segment. What will I do to it that will say this is a packet? Just like when I receive a packet in data link layer, I added source and destination MAC address with preamble starting and then ending. I said this is a frame. So in the case of the network layer, when it's accept the data, when has been encapsulated as segment, which is the PDU, as we call it in transport layer, the upper layer, when it receives it, it just receives it as a segment like this. Then this will now add the IP header. When it adds the IP header which will be the source and destination, the type, the version, etc. etc. So this, after adding this IP, it has now become a packet. When it moves to data link layer, it will now add destination and source MAC address and some other things, and then it becomes a frame. So this IP can be IP version 4 or version 6, depending on what you are using. We have been using version 4, but now we are moving to version 6 because version 4 is almost finishing, and then the newer version has been created to solve our problem. IP packets will be examined by layer 3 devices. So the devices that handle IP are routers. There are 3 devices. The devices that handle frames are switches, which are the layer 2 devices. When we say layer 2 devices, we're talking about data link layer, the second layer. When we say layer 3, we're referring to network layer, which is the third layer. When we say layer 4, we're referring to the transport layer, which is the second. So here it says IP address does not change. And NAT may, we will see this later, I think in scene 2 or 3, detail of how NAT may change IP. But for now, just hold in mind that it doesn't change. So for example, what it means that it doesn't change is that if you have a PC, a source, and let's say in between you have a switch, you have a router, let's say you have a router, another router, and then you have your destination. So this is the source, this is the destination. So the MAC address here is A, the MAC address here, for example, is B, the MAC address here is C, and the MAC address here, let's say, is D. The IP here is 1, the IP here is 2, the IP here is 3, and the IP here is 4. What he's saying is that IP doesn't change. If this guy says the source IP is 1, the destination IP is 4, the source MAC address will be A, and the destination MAC address will be B. So when the traffic comes here, the destination MAC address will be, so source IP is A, this guy, destination IP is this, maybe facebook.com, so it won't change because you are finding a way to reach Facebook. And then the source IP, the source MAC address is A, destination MAC address is B, is going to be of this one. When the traffic comes here, the source MAC address will remain 1, the destination MAC address, the source IP will remain 1, the destination IP address will remain 4, the source MAC address, let me repeat it. The source MAC address here is A, the destination will be B, the next device. The source IP is 1, but the destination will be the IP address of where you intend to go. When the traffic comes to this next device, the source IP will remain 1, the destination IP will remain 4. But the source MAC address will now change to B, the MAC address of this device. The destination MAC address will now be the next device, which is C. When it comes here, the source IP will remain, destination IP will remain, but the MAC address will change to this one, and destination MAC address will change to this one. So what is this IP? Now we say when we add the source and destination IP addresses, we have created a packet. So how does this IP operate? The characteristics of IP is that it is connectionless, best effort, and media independent. Connectionless means that if you have your devices here, you just connect to a network, and this network is connected to another device, connected to another device, connected to another device before it eventually reaches the destination. This is the source. The connectionless aspect is saying that you do not go and create a connection from the source to destination before you start sending information. You just send it. Because I have a connection to next device, I just send. This device will send. This device will send. This device will send. It doesn't mean that I must first create a connection, then I start sending my information. No, my information will go together with the available connection that I have. The second one is saying best effort delivery. Best effort means that I will not give you acknowledgement. It means it will not inform you that, look, your information arrived at this device, so you are acknowledging. Now it has arrived at here, get acknowledgement. Now it has arrived here, or it says until it reaches destination and the device will give the acknowledgement. There is no acknowledgement in IP because we're interested in low overhead to move it as fast as possible. So another protocol handles acknowledgement. So it doesn't mean that connection there is no acknowledgement. In general, moving from one device to another, there is acknowledgement. So In general, moving from one device to another, there is acknowledgement, but it's not going to be handled by this layer, by IP. So now, if source, and the last part which says media independent, it means that from the connection from this guy to this guy can be wireless. The connection here can be copper, maybe let's say UTP itself, copper UTP. This can be copper STP. This can be fiber, for example. So this is a different media, this is a different media, this is a different media, and this is a different media. Media independent means that it doesn't mean that from the source to destination it must be all wireless. Or let's say if connecting from Nigeria to Kenya must be wireless, or to Uganda must be wireless, or it must be fiber, or it must be... No, it depends on what the ISP used to connect. And whatever the ISP used to connect, the IP finds its way to the adjust. We said it does the encapsulation. When source is sent and this guy receives, it opens and says you came from wireless, so I will re-encapsulate you into UTP copper cable, what it can understand. Here it says you come from a UTP copper cable, so I will change you into a form that STP copper cable will understand, which normally is the same. Or you come from an STP copper cable, you are going out of fiber, this device will now re-encapsulate you into fiber. So it doesn't say it must be all through media, let's say wireless, copper, etc. Now, going further on this is our best effort delivery that it says, just like you are sending a mailbox, you don't go and check before you start sending your letter. You just go to the post office or to your mail output, you put it there and they pick. And then second part, we say best effort delivery says, I'm not going to do any acknowledgement. I will just send in as much as I can. I'll try my best, but there will be no guarantee of delivery. But I'll try my best. So what is going to handle guarantee of delivery is the upper layer protocol, but it's not going to be done in IP. IP is fully concerned in how fast can I move from source to destination. Media independent, we said the connection mustn't be all copper, or the connection mustn't be all wireless, or the connection mustn't be all fiber. It can be a combination of all, and then IP will find a way to do it. The devices know how to change from copper to serial, to fiber, to copper, and then to wireless, as the case may be. So in IP addresses, this is how the header looks like. First of all, routers do IP. The network devices, it is a router that handles and works with IP, while switches handle and work with MAC address switches that are linked there. So this is the format of IP. It has so many information, especially IP version 4. It has so many field 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So many of them. So, but the most important here, you look at the version, meaning is it version 4? Or who is the source IP and who is the destination IP? If you're going deeper, you can look at differentiation service for quality of service, identification, time to live, how long will it to the main person from one router to another. But let's stick to 1, 2, 3 that they have highlighted. So version, whether it's IP version 4 or IP version 6, and then the source IP, where is it coming from and where is it headed? So many options. So IP address, these are the details of the option. Differentiation service, like I said, for quality of service, to give priority of video over voice over data, as the case may be on your own network, and the version, whether it is IPv4 or IPv6, checksum to check if it has been corrupted, time to live to count how many times it can be passing, because we don't want the traffic that is lost roaming around the internet, and then the protocol that is connecting then the destination IP. So we also have now version 6. IPv6 and IP version 4, they can work the same on the same organization together, hand in hand. It means an organization can configure both IPv4 and IPv6, which is called a dual operation. And then, so now the IP here, what they call it, sorry, discarded. So here, IP version 6, here it says IP version 6 is as a result of IP version 4 being dilapidated, about to finish. For the depletion of it, and the problem it introduces when you're using NAT, we say NAT better. So just know that it's something NAT somewhere around the line. We'll talk about it. So, and it's about to finish that IPv6 came in. And IP version 6, what it does is IP version 6 can connect. The theory is that take a look at this. The theory is saying that we have 1,000, which is 10 raised to the power of 3. We have 1 million, 10 raised to the power of 6. We have 1 billion, 10 raised to the power of 9. We have trillion, 10 raised to the power of 12. We have quadrillion, we have quadrillion, we have septillion, septillion, quindecillion, up to 10 raised to the power of 33, decillion. And then we have 34, 35. IPv6 is on decillion, 10 raised to the power of 36. The huge IPv6 addresses that has been created, the theory is saying that for every grain of sand, if you just walk out of your home now or office and pick a grain of sand, we have enough IP to give it. The why this is done like this is because, you know, when internet started, it wasn't built for this number of people, and everybody now is connected, so the number of available IP is about to finish, and that is why it has been addressed in IPv6 to create more than enough IPv6 that no matter how many devices we connect, we cannot finish. So that is why we say we have enough IP that even if you take every grain of sand, that grain of sand will have an IP. This is how I want you to just imagine the number of IPv6 address that we have. So IPv6 address also, to reduce the number of overhead, it reduces the number of options it has in the header. So the header is lighter. It doesn't have so many information. It's only talk about the version, the traffic class for quality of service, flow levels, payload, what kind of packets I'm stating, and source, destination, IP, what is the next header, next device, for example. So, and this is the example for it, which is the next header protocol that has been encapsulated: TCP, UDP, hop limit, like we have TTL. How long will it remain on the internet? Roaming around. So what happens is the TTL or the hop limit is from one router to another -1, normally from 255 to the next router -1, which is 253. When it reaches 0, whichever device receives it at 0, it automatically drops the packet. So every host or what they call it, we're about to finish, just humor for a few seconds, for a few minutes, sorry. Every host or a router on a network, it does forwarding. Forwarding is moving traffic from one end to another. Now, how can it forward? For example, a PC here can forward to itself, which is the loopback address. So, you know, we said earlier in some of the lecture that ping is used for testing connectivity. Let's say I have a connection like this, but I want to test from this PC1, do I have connection to PC2? I can say ping the address of PC2. If I get reply, meaning that my connection is okay. If I ping this server and it replies, it says that I have a connection to the server. So now, if I ping 192.168.1.1, and if it happens to be my IP, then I'm pinging myself. Or I ping 127.0.0, which is a loopback address, I am pinging myself. But if it's an IPv6 colon 1, if you ping it, you are pinging yourself. Sometimes people ping themselves because to test the connectivity, whether their own network interface card is okay. If it replies, it means your network interface card is working fine. Another kind of connection can be local. We said a connection within an organization is local, while a connection outside an organization is remote. So if you have a connection here, that connection is local. If you have a connection here, it's local. Because you have a router in between, I said that a router is capable of connecting two or more networks together. So when you have a router, you see a connection to a network, a connection to a network. This router is connecting network 1 to network 2, organization 1 to organization 2, so two different. So any connection outside this to a different network is called a remote connection. Any connection within your own network is called a local connection. So this forwarding, okay. So what will be the scenario? Let me see. Okay, I can go back. So what this is saying is that if I have a connection, I have my PC connecting to a switch, connecting to another switch. Any connection among these guys is local connection. So all I require is the MAC address, source MAC address and destination MAC address. If I cannot find the destination MAC address, I will send it as all F, and this switch will help me find it, and then I can send to this thing. But if it's a different network, so this is network 1, and this is network 2, or organization 1 and organization 2, so there is a router. It means that, see, there will be a connection to this router. This router is called the default gateway. Now, the concept of a default gateway is host. require a default gateway when they are connecting outside their network. If they are connecting inside their network, in fact, they don't even need IP. They can use the MAC address to locate each other. But if they are connecting outside their network, they must find the IP address of the default gateway. And most of the times when we are assigning IP address to host, we give it its IP. We give it its subnet mask. We also give it the default gateway, saying this is your IP, one, your subnet mask, and then this is the default gateway. Default gateway is the address of the router, the interface of the router, from which you can exit out of the network. So if you see any traffic that is not here, which means the switch cannot handle it, send it to this router using the default gateway, and the router will find a way to reach it. So when a connection is local, it's yourself, you are pinging yourself. When it's local, it's within a network. When it's remote, it requires a default gateway so that it will go to the router, then the router will send it to whatever network. Why is it going to the router? Because it is a router that can connect to more than one network at the same time. So here, if you want to see, every host has its own table, app table to see the connection. And again, in IP version 6, it uses router and to request for the default gateway and then router advertisement to receive default gateway. So if you are on your PC, just like we exemplified earlier about pinging, you can touch your Windows key, type command prompt, and when you go into it and say net start -R, it will tell you the local routing table of that machine, all the IP address that it has, and the MAC addresses. So, and the MAC address. So, in an effort to round it up, so what is this routing? We said routing is a process of moving traffic from source to destination. Process of moving traffic from source to destination. Now, here, when you have this PC and it comes to this router, it is up to this router to find out that what is your destination when it opens it. It says my destination is, let's say, 1.1.1. It looks at that on my router, on my routing table, where is 1.1.1 connected to? So let's say, for example, if there is a link here. So 1.1.1 is connected to this link and not this link, so it will have to send it to this one. So if at all it's going to, let's say, 5.5.5, and it's here, it will look at the routing table and send it. So the routing table is where we keep the entry, the map of how to reach all networks. But when I receive an information, I look at the destination and I see which of the ports is connected to this destination, then I'll send it this way, or is closer to this destination. So again, after that, in the routing table, you can have different types of information like directly connected, remote, and default route. So a particular router in its routing table will have a directly connected. When we say directly connected, this router is connected to two devices. So this is directly connected to this router, and this is directly connected to this router. If you are taking it from the perspective of router 2, this network is directly connected to it, and this network is directly connected to it. And the internet is also directly connected to it. If taken from the perspective of router 1, network 10.0 is directly connected, network 209.168 is also directly connected. So from the perspective of router 1, what about this network? 10.1 is remotely connected. Any network that you can reach through another network that you are directly connected to is called remotely connected. This is a remote network. Directly connected from this perspective is the one that is directly connected to your interface, while remotely is the one that you can reach via a network which you are directly connected to. So if this one, say for example, I have another network X, from the perspective of router 1, network X is also remotely connected because it's not directly connected to this router. So on this route, how can this router build the routing table? It can be manual or it can be dynamic. Now, when it is manual, it means that the administrator will configure and say, if you are going this way, follow here. If you are going to, let's say, network 5, follow here. So the problem of static is if you say it should follow here, it will continue following here. Even if there is a problem, it means it will not readjust. But I have another part to the internet. If the traffic comes from this end and comes to this router, it can follow here to go to the internet. It can follow here and also arrive at the internet. If you configure static route, you're saying that it should be following here. If you configure it to be following here, you're saying it should be following this end. The problem is whether you configure it to follow here or to follow here, if it's down, it will not automatically change. But if it's a dynamic configuration, if this one is down, it automatically change and follow this way by itself. When this one is up, it can come back or it will do load balancing, sharing the traffic some via this route and some via this route. So this is the explanation that just like we said with the static, you tell it where it go. And then for the dynamic, it will be adjusting, it will be exchanging information amongst itself. When this link fails, it looks for another alternate path to deliver your information. And okay, we'll go back to the routing table. So we have talked about this MAC address and an IP. What is the difference between a MAC address and an IP address, and where do we use them? That is the last few slides that we need to talk about. So talking about IP and MAC address, we said MAC address are in layer 2. They are done with switches. When you have a switch connecting devices, what they're using to make their decision is the MAC address. But when you have a router, it means that you are connecting a different network to another different network. So what you use there is the IP address. So moving forward on this is saying that where do they play in hand? I've explained this using the packet tracer, which is called ARP, but I'll explain it here also again. Every device will have a MAC address. During the time of manufacturing, the manufacturer will assign MAC addresses on the network interface card. Any device you are able to connect to a network with, it has a network interface card, and that is done. So it is that MAC address that it will use to communicate to this using this switch within this LAN, and also in this LAN, it will also use the MAC address to communicate. But if it's connecting to different network to another different network, you need at least a router, and in this case, we have 2 routers. So what happens here is we say, if you have a source of 10, then 919.2.10, and then destination 10, which is, let's say, this guy, and source is this guy, the MAC address is AAA, because the destination is on a remote network, so it's giving the MAC address of the default gateway. We say a connection can be to itself, can be locally, or can be remotely. When it is locally, it means it's connected with a switch in the same network. When it's remotely, it means it's going to outside this network to a different network. And whenever traffic is leaving a network to another network, that traffic must have a default gateway or must pass through a router. So, and that is why here in the MAC address is given the MAC address of the default gateway. When it arrives here, the information, the source MAC address will change to this C, and then the destination MAC address will change to the next one. When it arrives here, the information, the source MAC address will change to this one, and destination will change to this one, but the IP address will remain. I was coming from this guy, and I'm still going toward this guy. And in ARP, which we have also talked about, is if I'm trying to identify somebody, because most of the applications, they use IP, you go to your PC and you say ping a particular IP, and the switches don't do IP address, they do MAC address, so they will use ARP, address resolution protocol. They will send a broadcast asking, who has this IP? Give me your MAC address. I can only use MAC address to communicate. Somebody wants to communicate to you. So if this is 1.5, 1.6, 1.1, 1.8, when this guy
now, so we'll pick up from that point of the relationship between MAC address and IP next week, just to try and interpret how layer 2 connects with layer 3, that is data link and network layer. How do they connect? How do packets move to become frames, or how do frames move to become packets, depending on whichever direction that you are taking in that communication process. Okay. Now, so that's overview of that's not an overview, but a deep learning on how layer 2 operates specifically, because that is what has been touched on. We have the switching methodologies or the switching mechanisms, cut through, fast forward, fragment free, and so on and so forth. Okay, so it summarizes how data link layer operates. What is a MAC address and Now, if you do that with the connection of what we did in the mathematics perspective, then you understand what we're really talking about. Okay, so unless there's a question, I'll end today's lecture at that point. I'll end today's lecture at that point. Kindly always visit your NetCard account, do the chapter exams. On your ZDS portal, I've also posted the PowerPoint notes there. You can download them if you need to go through them again. The video link will also be there, so you can also get in touch with that and move forward with it. Yes, any question? Question? Any question? Yeah, if there's no question, then we can stop there for today.